So this will be a short video on energy efficiency of mechanical interactions. So let's begin with a short example. Okay, so let's say we have a block and we want to push it to the right. So we apply a force that's directed towards the right. Okay, so when you want to push the block to the right, you'd also have another force acting on this block, right? Well, let's only speak about horizontal forces here. So we would have friction opposing this push to the right when the two surfaces rub against each other. And with this frictional force, we also have little bits of energy transformed into heat. And more often than not, you might experience this in real life. You'd also hear sound as well when you push an object, which is opposed by friction. Okay, so the key thing to note here is that some of our mechanical energy is converted into heat and sound. So while this happens, heat and sound aren't very useful for pushing the block, are they? But at the same time, you can't really convert this heat and sound back into mechanical energy, which is a bit of a problem for us. So we need to account for this in our calculations sometimes. Okay, so now we have the energy equation here. So efficiency is equal to useful energy out over the total energy in. So let's get a bit of the housekeeping out of the way. So we have energy efficiency. It's a dimensionless ratio. You just need to multiply by 100 if you want the percentage. Okay, so this also checks out because the numerator and denominator on the right are both in joules. When you have joules divided by joules, you just get no dimensions. And it's also good to note that on the left, efficiency is denoted by the Greek letter eta. It's not a letter N. Let's start with a simple example. So let's say we have a tennis ball and it's dropped from 2 meters above. And after this, we release it from rest and it rebounds 1.2 meters upwards. So what would be the efficiency of one bounce? So we know that the total energy at the beginning is just gravitational potential energy since it was at rest. And gravitational potential energy is just mg delta h. Delta h is 2 meters initially, and we're not sure what m is at the moment. And we can just leave g as the letter because it's a gravitational constant. We can use 10 or 9.8, doesn't really matter. We'll see later on. Okay, so we also need to know the total energy after the first bounce at its peak height. So we know that it bounces 1.2 meters up, so delta h is now 1.2 meters. And m and g we still don't know, but at the peak of its first bounce, the kinetic energy is also 0. So the total energy is just, again, the GPE. Okay, so the efficiency is denoted by the energy output, which was 1.2 mg, over the total energy input, which is the initial energy of 2 mg. So when you take this ratio, you can cancel out the mg's, which gives us 0.6 or 60% efficiency. So once we know the efficiency, we can work out, let's say, the maximum rebound height on the third bounce. So we have an efficiency of 0.6 and an initial height of 2 meters. So we saw from the previous problem that the height of the ball is only dependent on the gravitational potential energy, and the resulting gravitational potential energy is only dependent on the efficiency. So the height for free bounces would just be the initial height multiplied by the efficiency 3 times for free bounces. And this would just give us 2 times 0.6 to the power of 3. And so after our third bounce, we get a maximum height of 0.432 meters. So this concludes this brief introduction on energy efficiency.